Hi, I am Nikhil Jaiswal here to present our work on the document level translation task which was organized by WAT 2020. So the title of our paper is Improving NMT via Filtered Back Translation. So first I will give a brief summary of the task. So given a business scene dialog corpus or the BSD corpus, we need to translate the English sentences into Japanese and vice versa. So here is one such simple example from the corpus. So as we can see that it consists of multiple conversations and each conversation consists of several turns. So we need to translate the English sentence to Japanese and the other way around. And these are the statistics of the BSD corpus where we had around 20k sentence were for training, 2k for development and 2k for test. So although it was a document level task, we tackle this task as a sentence level NMT. So in order to do this, we applied several domain adaptation techniques. So first of all, we collected several publicly available open domain parallel corpora and we trained two different models, NMT models on this corpus. One is in the source to target direction and other is the target to source direction. Once this model was trained, we fine-tuned this model on the available BSD corpus data. And then when you use this fine-tuned model to translate the BSD test sentences. So this was our first model, also known as the base fine-tuned model. In the second approach, we took the advantage of the available monolingual data and we used the source monolingual data and pass it to the trained source to target model in order to generate the synthetic target data. Then we use these pairs to create target to source pseudo parallel data and we take an equal amount of true data which is from the open domain and then we shuffled this data and fine-tuned our target to source model. This was further followed by fine-tuning on the available BSD corpus and then we used this model to translate the BSD test sentence. So this model was also known as back translated fine-tuned model. In the third approach, we filtered the noisy sentence pseudo pairs using a filtering techniques and then we again collected an equal amount of open domain data and we merged this data and fine-tuned our target to source model. Then we fine-tuned again this model on the available BSD data and translated the BSD test data. So this was our third approach and was known as filtered back translated fine-tuned model. So moving ahead, for the filtering task, we applied a sentence level based similarity technique. So first of all, we calculated the sentence embeddings of the source and the language sentence using multilingual universal sentence encoder and then we calculated the cosine similarity score between this. So based on the available training data, the true data as well as the English Japanese back translated and the Japanese English back translated as well as the BSD corpus data, we determine the threshold for this cosine similarity score. So this pie chart basically denotes the different amounts of data based on the different threshold range. So I will demonstrate this using an example. So suppose this is our training data and as we can see that for a English sentence we have the corresponding Japanese pair. So we calculated the cosine similarity score between the sentence embedding and for example the cosine similarity score is 0.49. What we did next is that we took in order to determine what exactly this cosine similarity mean, we took the help of Google Translate and translated this Japanese sentence into English. Then we can see the whether this our original English sentence and the Google translated sentence match or not. So as we can see that when the score is less, though there was quite a difference in the meaning of the sentences. Similarly, we test for the higher score, so between zero point 0.5 and zero point 0.6, which is denoted below. So here there is slight improvement, but again the meaning is different. Then we again improved, checked the sample of the sentences where the score was between zero point 0.6 and zero point 0.7, and as you can see that when the score is increasing, the meaning of the English in the corresponding Google translated Japanese sentences are more are becoming quite well. Similarly, when the when we tested on the higher scores, so here we can see that yeah, there is a good amount of similarity between those two. So based on this criteria, we selected the threshold and filtered out the noisy pairs. We also use these threshold techniques to filter the true parallel data. So since we need an equal amount of true data corresponding to the pseudo parallel data, so what we did is that we sorted our true parallel data based on the decreasing order of the similarity scores, and we did some pre-processing such as the removal of pairs where the same text was present in the English and the Japanese column, as well as the such pairs where the same language were present. So these were due to the noise in the original data sets. And after doing all this kind of pre-processing, we basically returned the top n rows where n was equal to the number of pseudo-parallel sentences. So coming to the experimentation techniques, our first task was to train an open domain NMT model, and for this we collected several publicly available English-Japanese datasets. So we collected this and we merged this to create our training datasets of around 8 million sentence pairs and the validation set of around 10k and test set of 7k pairs. For the pre-processing part, we followed different pre-processing in both the directions. For the Japanese English, first of all, we calculated the BP on the raw text, and this was used to train the deep learning model. But for the opposite English to Japanese case, first of all, we tokenized the raw text using Moses and Kaiti tokenizers, and then BP was applied on this. Coming to the results on the open domain datasets, so we evaluated our open domain NMT model on several publicly available datasets such as MTNT, IWSLT 2070, WMT News, as well as the BSD datasets. So, as we can see from the table that the filtered back translated pair outperforms both base as well as the back translated models in both the language pair directions. Then we calculated our results on the BSD test data. So there were two different settings. One was the constraint in which we are not allowed to use any external data. So for this setting, we trained two-layer transformer models as well as three-layer transformer models, and we also did an ensemble of these models using the checkpoint ensembling. Also, we tried to fine-tune MBART on this, and from the results, as you can see that fine-tuning MBART outperforms every other approaches in these scenarios. For the unconstrained case, we had three different models, the base models, then the back translated and the filtered back translated, as well as the ensemble models combining these different techniques. So we found out that the ensemble consisting of base and the filtered back translated outperforms every other cases. And in the top right corners you can see the human evaluation results. So out of 5 we were able to obtain a score of greater than 4 in both the directions in the unconstrained settings. So with this we would like to conclude our experiments. So we experimented with several techniques in both the scenarios, and for the constraint settings we found out that fine tuning MPART gave us the best performance, whereas for the unconstrained settings the ensemble models consisting of the base and the filtered back translated models gave us the best results. And we also showed that by using a simple ensemble techniques of averaging checkpoints, the translation performance could further be improvised. That's all. Thank you for hearing. Thank you.